All right, welcome to your AP problem stoichiometry walkthrough. I'm going to go through one conceptual question because we did quite a few questions in class, and then I'm going to hit up some AP. Okay, so question 15 on page 7 asks us a solution containing 15.2 grams of barium bromide, an ionic compound, is reacted with a solution containing excess sodium phosphate to form 9.50 grams of precipitate. What is the percent yield of the reaction? Begin by writing a balance equation using a solubility table. So first and foremost, you should notice immediately in the question that you, one, have a double displacement reaction between two ionic compounds. And two, you more specifically have a double displacement. You have a precipitate, right? A precipitate producing reaction. So according to our solubility rules and according to our balancing, you would get the following reaction. 3BaBr2, barium bromide, aqueous, reacts with 2 sodium phosphates, aqueous, to produce barium phosphate, solid precipitate, and 6 sodium bromides aqueous, i.e. dissociated, okay? So I'm not really going to go through balancing and I'm not really going to go through writing that reaction because I assume now that you're at the point where you can write a chemical formula based on the name. And I assume that you're at the point where you can balance according to law of conservation of mass and determine your coefficients, i.e. your molar ratios. Okay. So once I get this, what I know is that I'm told that the excess is sodium phosphate. So what I'm told is I actually don't have to worry about my sodium phosphate being at all the reagent that would determine how much actual product I could get. Okay. And I'm also told in my details that I do get 9.50 grams of this. But the question is, was that the maximum amount? Was that the theoretical yield I could get with it, with this reaction, particularly given 15.2 grams of barium bromide? Or was it only a portion? Hence the question about percent yield. Did I get all that I could out of this reaction, realizing that the way the question set up is that I am limited by 15.2 grams of this reactant. So what I need to do is I need to go through a stoichiometric process of, well, what was my theoretical yield according to my limiting reactant? Because if I have excess sodium phosphate, it's basically like whatever, like that's not the problem here. But the problem is do I have enough barium bromide? And so what we're going to see is, well, what should we have gotten with this amount of barium bromide? So we will set up our stoichiometry with what we know, which is 15.2 grams of barium bromide. And we know that if we're going to switch between, right, grams of one substance, barium bromide, to theoretical grams of our product, barium phosphate, we need to go through the mole first, right? So we're going to turn this into a molar amount. So we're going to use the molar mass of barium bromide, which is 1 mole of barium bromide, has a gram amount of 297.13 grams of barium bromide. Okay. And once we do that, we've canceled out our grams of barium bromide and we're left with moles of barium bromide. So then we move on to the next step and we say, well, according to my molar ratio, my balance coefficients, my balance equation, I know that for every 3 moles of barium bromide, I produce 1 mole of barium 3, right, PO4, 2 barium phosphate. Okay, and so that gets me into not moles of barium bromide, but now moles, and I forgot to write the word moles, of barium phosphate. And once I'm in moles of barium phosphate, now what I can do is say, okay, well, theoretical yield is calculated in grams as a percentage. And so, and also like my actual yield, right? This is my actual yield. What I actually got in lab is reported in grams as well. So I know I'm going to have to get the final value in grams to make a comparable conclusion or a comparable analysis. And so I'm going to use the molar mass of barium phosphate which is for every 1 mole of barium phosphate, I have 601.93 grams of barium phosphate. And that gets me a final answer of, I theoretically should have gotten from 15.2 grams of barium bromide, 10.3 grams of barium phosphate. Okay, so then what I'm told is that's not my final answer, because in the end I was asked what is the percent yield. So now I go over and I say, well, percent yield is equal to actual over theoretical times 100. So we would say it's equal to actual was 9.50 grams over 10.3 grams of barium phosphate, and I'd get times 100 that my percent yield was 92%. Okay. And you might have rounded slightly differently, but the AP actually reports to okay. Yep. Okay, perfect. We're just gonna leave it there. I don't know why it reports only to 2 sig figs. The way that this question was written was 3 sig figs. I wonder if my TAs accidentally mistyped it. Anyway, that's the big idea right there. If you wanted to find the error, just as a little bonus, what if I asked you what was the error margin? Or, the error, percent error is whatever you didn't get, like how much of what you didn't get over the whole. So it would be 10.3 minus 9.5 all over 10.3 times 100 would be our error margin. Like how much did we not get? How much of that percent? Yeah, I think I'm just repeating myself. We'll just leave it at that. And that would have been 7.77% for error, percent error. Totally not being asked in the question, but I just wanted to mention it and tack it on because it could be a common like portion in an FRQ. And I'll change the color to one that is not so similar. And I'll try to shrink it too. There you go. For just like a little bonus. Okay, so let's go ahead and move on to AP questions. So we're gonna do a part of AP, one long FRQ, which is of course 23 minutes, worth 10 points. Okay, and then we're gonna do, I think, a full short. So what I'm gonna do is I'm gonna kind of pick up where I left off with question 3. We've determined our molar ratios already, and now we're asked to look at the particulate diagram. And what we have is a particulate representation from before and after the reaction is shown below. The contents of the container before the reaction are represented in the box on the left, and the contents in the container after the reaction are shown in the box on the right. So, answering the questions, a student claims that N2 is the limiting reactant. Do you agree or disagree? Justify your answer. So, what we see here is, according to our reaction, we need 4 Qs for every 1 N2. So in our thing, we have 4 Qs, 1, 2, 3, 4, 5, 6, 7, 8. So here we have 8 Qs. And here we also have 2 N2s, which, by the way, simplifies down to a ratio of 4 Qs and 1 N2 being represented in this before reaction. So what we see is our ratio of reactant species is matched or aligned with the stoichiometric ratios necessary for the reaction. 4 Qs for every 1 N2. And then what we see is on the reactant or the product side, we see that we get for every 4 Qs and 1 N2 reactant, we get 1 N2 Q4s. So here we have 1 N2 Q4 and 1 N2 Q4. So we have 2 N2 Q4s, which would be equated to, according to the multiple that we have, like saying 1 N2 Q4. It matches ratio wise. And let's see if I can maybe change the color just to offer a little bit of more support of how to think about this. style, this will be black so that you see that this is the original ratio. So what we see is our picture, our particulate diagram, actually represents the exact stoichiometric ratios that we would expect for this reaction. So a student claims that N2 is the limiting reactant. Do you agree or disagree? Honestly, the AP would accept both, agree and disagree, because you could say, oh, I disagree because neither reactant is used up first as the particles present are in the same ratio as the balanced chemical equation. Okay, that's totally valid. That is one totally okay answer. The AP would also accept you saying agree. And here's why. You could say agree, okay, because according to the stoichiometry, right, according to the molar ratios of the balanced chemical equation, according to the ratio of the balanced chemical equation, N2, okay, ooh, you know what? That's kind of interesting. You know what? I'm looking at the AP answer and I actually kind of disagree with how they phrased it because I don't think it actually makes as much sense. So when I look at this, I think it's actually better just to say disagree. I think it's better just to say disagree. I'm looking at the AP answer and they're saying that they'll accept agree or disagree, but I find that the agree are not as compelling. A justification for the agree is not as compelling as disagree. So I'm actually going to leave you at that. And apologies for the confusion. But yeah, I actually think disagree is the most logical answer. They do, if you look at the workbook key, they do offer an agree from the AP answer key that is acceptable. However, I think it's more palatable and logical to say disagree because you simply don't have any amount that's used up first. And I would say that theoretically it should be Q that would, if we're just looking at molar ratio wise, like no gram amount given, just generally molar ratio wise, we would think that Q is actually the limiting reactant because of its larger molar ratio required or stoichiometric coefficient, right? So I'm going to leave it at disagree. And let's go ahead and move on. So in a different reaction, N2 reacts with pure metal, X, to form the compound X3N2. Which of the following three complete photoelectron spectra could be that of metal X? Justify your choice. So when we look at this question, it's really important for you to note that this is unit 1, PES, photoelectron spectroscopy, where we are shooting energy with high energy beams. We're shooting electrons off the rings of an atom or the energy levels of a respective atom, and therefore marking the electron configuration of that atom. Okay, we're basically determining it. So what we have here is we need to realize that I would just say start drawing or writing out the electron spectroscopy of each element being represented or electron configuration. So we got 1s2, we've got 2s2, we got 2p6, and we got 3s2. Okay, so you know that one is spectrum. One here, we theoretically, I'm not really sure what's happening in spectrum two, considering that the binding energy is so different. But theoretically, this would be 1s2, 2s2, 2p1. And this is 1s2, 2s2, 2p6, 3s1. Okay, so what we have here is the element for 3s2 is magnesium. The element here for 2p1, ending at 2p1, is lithium. And the element here ending at 3s1 is sodium. So when we look at these metals, you got to realize this is going to be an ionic bond. So we're going to look at charge canceling. So the question is, how do our charges cancel? Okay, so when we have this equation X3N2, that tells us we know that nitrogen is always going to take on a 3 minus charge according to its placement on the periodic table and in regards to its ionic bond interaction. And so we know that if N2 is going to take on a 3 minus charge, that means the total charge that the anion nitrogen brings is going to be a -6. Well, we know then from the formula that whatever the charge of X is, it's got to be some number times 3 that adds up to +6. So we know then the number has to be equal to a 2 plus charge. So we would say spectrum 1 is our answer because spectrum 1 represents the correct, represents the correct metal, or represents the metal, most likely to form the compound X3N2 because, the formula implies an element that carries a 2 plus charge. All right. And spectrum 1 is the only element with 2 valence electrons. Okay. So D, a student claims that molecule X3N2 contains both ionic and polar covalent bonds. Do you agree or disagree? So this is an interesting question. Remember, an ionic bond, is based off of full charge transfer, and a polar covalent bond implies sharing. But what we see here is a metal plus a non-metal, and we see a required charge that we already addressed earlier. So therefore, we would say we disagree because, the compound is composed of highly, electronegative nitrogen with really low electronegative metal, therefore possessing a large electronegativity difference where electrons are exchanged and not shared. Okay, that's one way you could answer it. You also could say all of that and then blah, 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 blah. Therefore, possessing a large electronegativity density where electrons are exchanged and charges are, or you could also say, and charges are carried by the elements. Right? That's another way you could have said it. Okay, both are correct. If you wanted to and you wanted to be really, really thorough, you could add in the kind of clarity on what is a polar bond, right? You could even say an addition, right? Meanwhile, polar bonds share electrons. Polar covalent bonds share electrons, right? So you could do that. Either answer would be completely acceptable, okay? So a new triatomic element, A3, is discovered and is found to have a molar mass of 93 grams per mole. At high temperatures, A3 reacts with N2, molar mass of 28, to produce this compound N2A, as shown in the equation below. And they balance it for you. How lovely of them. So determine the mass of 0.25 moles of N2A. So what you need to realize is you are trying to determine the mass of 0.25 moles of N2A. So as far as our little map goes, we're going to go from moles of N2A to grams of N2A. It's the same substance. So all we're changing is between the moles and the grams. Well, that change should immediately make us think of molar mass as a conversion. And so what we need to do is simply determine the molar mass of our compound N2A, which for us would be if N2 is 28 grams plus A3 is 93. So 93 divided by 3 would give us the value in grams of just A, right? This is the N2 part. This is the A part. And we would find that our molar mass for the entire compound is going to be 59 grams per mole for the molar mass of the entire compound. So simply we would just then use our basic stoichiometry, 0.25 moles of N2A times the molar mass. For every 59 grams, I have 1 mole, and I get a value of approximately, according to sig figs, 15 grams of N2A. And we're going to stop here in this problem. Okay. So that is like a dream FRQ right there in terms of part E being really, really short. So let's quickly go over one more. And actually, you know what? I'm going to stop here because I think that's a really thorough example of between the conceptual and the FRQ portion of the long. And I'm going to leave it here because we don't have too many AP problems in this section. And so I want to give you guys ample opportunity to practice your own skills without me directing you in every step. So I believe the question 4 is the last question 5. We only have 5 AP FRQs in here. So, and we've gone through several already, and we're going to go through another one with the AP problem for the last unit of this subunit or subtopic of this unit. So I'll stop there, and good job, you guys.